Hello and welcome to the last 24 hours of GCSE. So I'm Lewis from Physics Online. I've got a website, GCSE Physics Online, with over 500 videos explaining absolutely everything that you could possibly need to know for GCSE Physics. Of course, that's too much to do tonight unless you basically stay up between now and your exam watching every video. But I just thought I'd do a last bit of kind of revision just to kind of really go over some of the more tricky areas that come up for paper 2. And I guess really the focus of the live today is going to be looking at AQA physics, and that's going to be, I think, the thing that most people are doing. So yeah, hello to everybody. Oscar, I guess you're an A-level person, Oscar, if you've just realised, yeah, this is now a GCSE live stream only. Hello, Matty. Hello, Soraya. Lots of people there also putting in the answer to the poll about are you ready for paper 2? So I think about 67% are ready for it. We'll see if that changes. But yeah, basically, we're going to just do maybe an hour and a half of final revision. It will be staying on YouTube, so if you need to come back to it later this evening, in the middle of the night, first thing tomorrow morning, it will be there. And also, because you're, I guess, the kind of people who are watching this, if you are thinking about doing A-level physics, then do it. It is a brilliant thing to be doing in sixth form. I also have lots of support. I've got videos that cover the entire A-level course in the way that I've done GCSE videos as well. And if you are thinking about doing that, I've got this book that you should probably have a look at over the summer before you start A-level physics. I've basically got questions every day, and these cover July, August, and then September and October. And this is just one of several books that give you questions for every single day of the A-level physics course. But the reason this is useful is because if you have a copy of the book that you can find in Amazon, I've got a link beneath the video. Basically, there's some questions that you should do every day in July, starting on the 1st. And if you just spend about 5 minutes a day doing a little bit of physics, revising the maths, developing your skills, it means that your start of A-level, the transition into year 12, is going to be super smooth, super easy. And you'll realise how A-level basically builds on everything you've been doing at GCSE. So yeah, this is going to be GCSE. This is going to cover the material needed for triple as well as double physics. So it'll be useful if you are doing the separate physics, sometimes called triple science, or it's also going to be useful if you are doing combined or sometimes called trilogy if you're doing AQA. And what I'll try and do is, as we go through the video, I'll just highlight the areas that only those doing triple science need to know about. Now, the basis of this is going to be AQA physics, because that's what I think about 80%. Actually, there's quite a few people watching now, about 50 of you already, so hello. Just let me know in the chat which exam board you're doing. So are you doing AQA, are you doing OCR, EdXL, IGCSE? Whatever it is, a lot of the content is going to be suitable for everybody, but this is really going to focus on AQA. So Soraya saying AQA, Rosie saying thank you. We've got Ligma, Sigma, OCRA. There will still be something here that's useful for you. Combined, says Joel Shah. Edward, AQA combined, says Helena. Yeah, so basically lots of different people doing all sorts of exam boards, but it's all going to be the same kind of physics. Now, what I'm going to do is I'm going to use this thing here, which is basically based on the AQA specification, and I'm going to go through sort of step by step the different areas. So we've got work on forces. There's then going to be a section on waves, quite a nice bit of the course. Then we've got probably the hardest bit, in my opinion, is the electromagnetism. And then finally, a little treat to kind of keep you going is a little bit about the space physics right at the very end. And so what I was going to do was basically just remind you about what you currently know. And of course, the main thing is that it's not just what you know, it's about how you apply your knowledge, especially in unfamiliar contexts. When there's questions that introduce new information, can you relate that to what you've already covered in class with your teachers? So let's just start here. So looking at scalars and vectors, well, basically a scalar is something that just has a size. So this could include things like speed, or you might have things like distance. These just have what we call a magnitude. So those are going to be scalar quantities. And a vector quantity is something that also has a direction, and that's where the direction is important. Velocity and displacement are basically things where we need to know maybe the direction that something's moving in. We might give it a positive or a negative value, or maybe an angle, for example. If it's a bearing, then there's going to be a displacement in a certain kind of certain bearing. Now, the way that we represent vectors is with an arrow, where basically the size of the arrow tells us about the size or the magnitude of that quantity, and of course the direction is important as well. Now, I should have done this better. Every time you draw something in your exam tomorrow, make sure that you use a ruler so you get a nice straight line. The length is going to be proportional to the size of that vector. Maybe it's the force or the velocity of something. So always draw stuff in a pencil just to stop you making any mistakes. Basically vectors, scalars, all good stuff. Now, a really important example of a vector quantity is force. And there are different forces that you need to be able to identify and label. Again, we often draw diagrams where we have arrows to show the size of different forces. Basically, the main types of force are, you've got forces which arise due to things being in contact. So these are our contact forces. So this is where you've got two surfaces. So this is where you might have friction between two surfaces. There might be air resistance, and that's because something might be colliding with particles in the air. You might have water resistance because of something moving through water and there's water particles colliding with it. We've also got things like tension, the normal contact force. And I think the normal contact force is the way that AQA phrase it. And basically, this is often the force between a surface and something it's in contact with. So if you've got something like a person stood on the ground, they might have a downwards force, but there's also going to be an upwards force of the earth pushing back up on their feet. So I'm just going to put that in red. This force here would be the normal contact force, sometimes also known as a reaction force. Now, the other force in this case here, the force down, would be, well, actually, what would we call it? What's the downwards force acting on a person stood on the ground? So yeah, while you're answering that in the comments, this is live. So hello, people asking if it's live or not. And of course, it will be up on YouTube after this. Weight, yeah, so the weight, you're doing really well. A lot of the time, people say the word gravity, which isn't what it should be. So don't say the word gravity as the downwards force. Basically, weight is a much better answer. And that's the force due to the gravitational attraction between two objects on that object that has mass. Now, weight is an example of a non-contact force. So there's going to be a weight force on you if you're in contact with the ground or if you're above it out in space. There's always going to be this gravitational force. The other types of non-contact force could be the electrostatic force between two charged objects, maybe a positive and a negative charge. We also have maybe the magnetic force between the north and the south pole. So these ones here don't need to be in contact, whereas other things like the normal contact force, you need to have things in contact. Hopefully that makes it seem easy. Cheesy Beans, great name. Is foundation included, David? Yes, it is. So everything I'm talking about here at the moment, everybody needs to know about. So there we go. Label it as weight, and there we go. I guess the other thing about weight, we can calculate the weight by multiplying the mass by the gravitational field strength. Now, the important thing, and this is like a common misconception because we always use the word weight when we mean mass and vice versa. Weight is a force and therefore it has the units of a Newton, whereas mass is just how much something has a mass, I guess, and it's got the units of the kilogram. And the gravitational field strength has the units of newtons per kilogram, which on Earth is about 9.8 newtons per kilogram. Just be aware if you're doing OCR Red Excel, sometimes they might use a value of 10. Okay, so just mass is something that is always going to be the same. I have a mass of about 88 kilograms, and I would have a mass of 88 kilograms wherever I went in the universe. However, my weight on Earth is going to be about approximately 880 newtons. But if I went to the moon, or if Elon Musk kind of took me out to Mars and it was where there's a smaller gravitational force, I'd have a much smaller size of weight. There we go, that thing there, pretty straightforward. And of course, what we often have in real life is we might have an object that has forces acting on it in all different directions. So maybe there's a weight force down, there's an up thrust, there's a drag, there's like some driving force, whatever it might be, and things can start to look a bit complicated. So what we tend to do is, and at GCSE you'd never get this many forces acting on one object, but what we can do is we can replace all of these arrows with the equivalent arrow that has the same result. So I guess this one here might be a resultant force like that. Okay, so the resultant force is basically the sum of all of the other forces acting on something. So a really nice example might be, imagine you've got something with a force of 3 newtons acting to the left, and there's a force of 7 newtons acting to the right. Well, basically you've got 7 this way minus 3, and the resultant of that is going to be 4 newtons to the right. Okay, so this is basically all we mean by resultant force. Occasionally, because you lot are now GCSE, you're kind of and obviously you can do this in maths as well, is there might be an example, maybe where there's a force upwards, maybe a force to the left, and the result of these two things is going to be upwards and to the left. And you can actually work it out by using a triangle. Often there's going to be a right angle triangle there, so don't forget what you've done in GCSE maths where you've looked at Pythagoras. So for example, imagine we had a 4 Newton force upwards and we had an 8 Newton force to the side. We could basically draw one force with the next force kind of added sort of tip to tail. And then you've got a right angle triangle where this side is 8 Newtons, that side is 4 Newtons. And the resultant, the hypotenuse, is going to be this length over here. And the size of that, let's just call that F. The size of this resultant force is going to be the square root of 8 squared plus 4 squared, which I guess is going to be, what, the square root of 80, is it? Okay, so 4 squared plus 8 squared is 80, square root that, and this is equal then to about 8.9 newtons. So that's how we can deal with the resultant force of two forces which are at right angles to each other. Okay, by the way, we will at the end, or later on, we'll be looking at slip rings and split rings and how that kind of works in maybe a motor or a generator on basically DC circuits or AC circuits. So we will cover that later, and I'll do my best to draw some pictures of them. Okay, so let's keep going. Yeah, it basically says here, use free body diagrams, which is just a diagram showing the forces acting on an object. Resolve a single force into two components that act at right angles to one another. So that's basically how much is a force to the right, how much is a force upwards or downwards. And then of course we can use vector diagrams to resolve forces. So this might be, maybe there's a scale drawing here. So make sure you do have your ruler and a pencil if it comes to drawing these kind of scale drawings. The next one, oh yeah, what angle is it for the direction? That's a good point, because I guess with a vector and a force, at GCSE they often just ask you to work out the size of the force. But of course, if we had that last example where we had 4 newtons upwards and we had 8 newtons to the side, if you wanted to work out the angle of this resultant force, you could then use SOHCAHTOA. Now this is something that you might do in GCSE maths, but it's going to be quite rare to have this asked in a GCSE paper, but of course a lot of you know it. This is the hypotenuse, this is the adjacent side, and that is the opposite side. And then using SOHCAHTOA, if you know the adjacent and the opposite side, we could say that tan theta is equal to the opposite over the adjacent. So that would mean theta is equal to tan to the minus 1 of 4 over 8, and that's just inverse tan of a half, which is equal to 27 degrees. Okay, but I suspect that would be quite a high demand question for GCSE. Okay, work done and energy transfer. Now, of course, you've already done paper one. You know from paper one that power is equal to the energy per unit time. And we can also say that power is equal to the work done per unit time. And you've already done lots of work looking at energy. Basically, if you do work on an object, you're going to be transferring energy to it. And there's another equation here that looks at how we can actually calculate the work done on the object. And basically, if you apply a force to something, the bigger the size of the force, or the further the object is moved, the more work or the more energy is transferred. And we can say that the work done is equal to the force multiplied by the distance travelled in the direction of the force. Okay, and that's what it says, again, in the specification that you should be kind of looking at. And then, of course, if we're thinking about the units, imagine you had a force of 1 Newton, and we multiplied this by 1 metre, maybe the distance that something moves, then this is going to give us the work done in joules, and this would give us a unit of 1 joule. So 1 joule is the same as saying a force of 1 Newton does work on an object over a distance of 1 metre, and that's going to be what we mean by 1 joule. Okay, right, there we go. Apart from that though, a lot of this stuff here about kind of work done is what you've already done for paper one. Then we have forces and elasticity, which again is something that you did previously, maybe when we looked at things like the elastic potential energy. But basically, if you have a spring and you apply a force to it, maybe by putting a mass on or putting on a weight, you see how the words are used sort of interchangeably. If you put a force onto this thing, then the spring is going to extend by a certain length, okay, by a certain value. And what we can say is that F is equal to KE, where K is just our constant of proportionality and it's our spring constant. So K is equal to F over E, and that means the units for the spring constant are newtons per metre. Okay, so this is basically how stiff that spring is. And don't forget that if you've got a spring, it can be extended to make it longer, and it can be compressed to make it shorter. So E could be the extension or just the amount that that spring is made shorter. Okay, whizzing through this. And of course, if you know we've got this equation here, don't forget that the other equation you need to know about springs is the amount of energy stored. And this elastic potential energy is equal to a half KE squared. So I can see that there's the potential for there being maybe a 4-mark or a 5-mark question about springs, where maybe first of all, they give you some information about the mass being added to a spring. If you know the mass being added, that means the force applied is going to be equal to the weight, which equals m times g, as we saw previously. That maybe allow you to work out the value of the spring constant. And if you know the spring constant and the extension, you can then work out the amount of energy stored in that spring. There we go, nice and simple. Now the next bit is something that you only need to know about if you are doing triple science, and this is to do with moments. So this part here, this work on moments, is to really look at maybe objects which are maybe rotating, or we've got something in equilibrium, which means the forces acting on it are balanced, and also the moments on that object are balanced as well. Now, the moment of a force is equal to the force times the perpendicular distance away from the pivot. Okay, so this distance here is going to be the perpendicular distance. And say, for example, we had something like this. There might be a pivot over here. I'm just going to represent with this small triangle. And if we had a force acting down here, the turning effect of that force, the moment, the turning effect of that force is going to be equal to the size of that force multiplied by the perpendicular distance away from that pivot. Okay, and of course, if you've got something which is perfectly balanced, we can say that this means it's in equilibrium. And for an object in equilibrium, the anti-clockwise moments are equal to the clockwise moments. So for example, we might have something up here where if there wasn't another force acting, this thing here just might start rotating. So what we might need is a much bigger force acting down here, F, but that's going to be acting at a much smaller distance, D. And so for this thing here, we could say that the anti-clockwise force times the distance is going to be equal to the clockwise force times the distance if it's all balanced and it's in equilibrium. And you can see a much larger force acts at a smaller distance will have the same turning effect as a smaller force acting at a much larger distance. Okay, is m equals f times d on your equation sheet? Yes, it is. Sometimes I think, I can't remember what it says, but basically the equations you need are going to be given to you. Okay, then we've got things about pressure. Now there's one equation that people sort of tend to forget, and it's just the simplest one. And again, this is something that you need to know about if you are doing triple physics. So if you're doing combined trilogy, you don't need to know about this. But you do need to know that pressure, for those doing triple, is equal to the force per unit area. Now we use a lowercase p for pressure, capital F for force, and a capital A for that surface area. And because we've got the force measured in newtons often, and the area measured in square meters, that means the units for pressure are newtons per square meter, or we can call this a Pascal. PA is Pascal. Okay, let me just have a quick look at the chat. It says here, who's on here because a certain teacher posted on a certain Google Classroom. Do you know, that's really good actually. If teachers are recommending me as a last bit of revision, that's brilliant. Yeah, so, okay, lots of stuff here, lots of good stuff here about moment is the turning effect of a force. Excellent, Sunster, yeah, perfect. There's also lots of stuff talking about DC generators and brushes and all that stuff. I will come on to that later, so don't worry, I will get on to trying to do a bit more explanation of, I think, the trickiest bits of the physics. And yeah, what's a dynamo? We'll come on to that later. Okay, so that's going to be the pressure at a surface, but sometimes what we think about is maybe a column of liquid. So let's imagine you've just got a simple measuring cylinder at school. As you go deeper down the measuring cylinder, there's going to be more liquid above an object. So let's imagine we've got an object here that started out up here. Now at the top, there's not much liquid above it, so there's not much force pushing it down. As we go deeper down though, there's going to be more liquid above it, and what we can look at is the change in pressure as something goes through a certain height. And the change in pressure is equal to h rho g. So h is going to be the height that something's moved under that fluid. P is the pressure in pascals. Rho is going to be the density of that liquid. And effectively, if you've got something which is more dense, like for example, if we were to push something under a column of mercury, it would have a much greater pressure at the same depth because it's a much denser liquid. And then G is our gravitational field strength. Okay, yeah, don't call it gravity, call it gravitational field strength. When they say liquid, do they mean fluid? Yeah, there's also potentially, we often talk about, in the specification, they do talk about a liquid. So yeah, basically this is the pressure due to a liquid. Yeah, so that's all you need to consider for GCSE, it's just a liquid. Yeah, that's it basically. The other thing is that if you've got something down here, although there might be a certain pressure at the top, because you've got something which is further down at the bottom than the top, there'd actually be a greater pressure at the bottom of this object than at the top. And because the pressure here is bigger than that pressure, that means the force per unit area at the bottom is going to be bigger than the force per unit area at the top. And actually, there's going to be an upwards force acting on this object. Now this upwards force, because it's acting upwards, is what we call upthrust. And this is something that you get in fluids, so gases and liquids. And it's basically sometimes also known as the buoyancy force, because this is a force that basically stops things sinking, or even if they are sinking, it still provides some upwards force. And yeah, there we go. Yeah, right. Cool. I think that's enough of that bit there. Also, it does say here, explain why atmospheric pressure varies with height above the Earth's surface. And I guess there's basically in the specification it says how at a lower level, so if we now think about the Earth's surface, there's going to be a higher pressure of air lower down because that's where air is denser. And then as we go higher up through the atmosphere, the density decreases until I guess you get to the edge of that where it's basically space. And what you need to know is that if you've got maybe a particle down here, it's going to have like a column of air above it. So there's effectively the weight of all of the particles above it which is pushing down. And that means we've got a greater pressure at lower altitudes. As you go higher and higher up, so let's imagine up here, there's going to be less particles above the air particles here. And that means there's going to be a lower pressure as you get higher and higher up in the Earth's atmosphere. And I think there's a good question a few years ago about the terminal velocity of a skydiver. Why is it that they went quicker when they jumped from a balloon that was much higher up in above the Earth's surface? And basically at higher heights, there's going to be less air particles and therefore there'd be less drag force, so somebody can have a higher terminal velocity. Okay, oh my God, there's so much to go through for GCSE, isn't there? Right, we're now going to come on to looking at forces in motion. And then, what else do we have? So we're going to do a bit of forces in motion, some motion graphs, and I think we've then got a little bit more about Newton's laws, a bit about momentum. Yeah, so basically not too much. So you need to know about certain values if you need to estimate maybe how quickly somebody's walking, what if they're running, or what if they're cycling. So these are the data quoted by AQA. So walking is about 1.5 meters per second, running is about 3 meters per second, and cycling is about 6 meters per second. So it's just to have an indication of those, the size of those things. And then we have the best equation, the most useful equation sometimes for GCSE physics, and basically it says that distance is equal to the speed multiplied by the time, or speed is equal to the distance travelled divided by t. Now, do not listen to your maths teachers, they're wrong. S is what we use for distance, so don't commonly use d for distance. V is the speed or the velocity. So v equals s over t, and of course t is the time in seconds. And we always want to use our standard units. So distance measured in meters, time measured in seconds, and therefore meters per second for our speed. And what we can do is have some graphs that kind of show this. So you might have a distance time graph, or you might have a velocity time graph. Okay, now let's imagine we had something that did this. The gradient of this line here tells us how quickly something is moving. So here we can see that as time goes on, the distance increases, the distance away from where we started measuring, and the gradient here of that line is equal to the velocity or the speed at that point. When you've got a velocity time graph though, here the gradient tells you the rate of change of velocity, and here that gradient is equal to the acceleration. So in describing the motion of these two similar looking graphs, we've got an object that is moving at a constant velocity, and then the velocity goes to 0. So we've got a flat line here, so the velocity is equal to 0, so it's been moving and then it stops. With this one, it looks like the same shape, but we're looking at different data. So this is something where the velocity increases and increases and increases, and then there's a point when it's not accelerating, but it's got a constant velocity. So that's that example there of a velocity time graph. The other thing that you can do is look at the area underneath the velocity time graph, and this area is equal to the distance that an object has travelled. Okay, right, okay, all good so far? Don't forget, of course, if you are doing higher tier, they may well give you a graph that has data that maybe has a curve on it. And if they want you to maybe look at the velocity at a certain point, what you need to do is you need to draw in a tangent to the line at the point that you're investigating. Once you've drawn the tangent, you can then work out the gradient to find the instantaneous velocity at that point. And for this one here, there's an equation that we can use that says the acceleration is equal to the change in velocity divided by time, which is basically what that gradient represents. The change in velocity over a certain time is going to be equal to the acceleration. Okay, yeah, all good so far? By the way, it's great to have so many people here. Some good questions in the chat, some nice polite chat, so it's good. I think that's basically all we need to know. Oh yeah, can I just show the hardest equation? So the hardest equation that there will possibly be in GCSE physics is v squared minus u squared is equal to 2as. Now, because it's a hard equation, I reckon the questions they might ask about where this is used are going to be relatively straightforward. The key thing is, every time you get a calculation, and you know this from doing your GCSE maths papers, is basically try and identify from the question the information that you've been given, the information that you're trying to find out, what the numbers might be, and then you can just put it into this. So this is obviously a really good example of where you can substitute your numbers in, then do a bit of rearranging to find the right answer. So we've got our final velocity squared minus the initial velocity, the starting velocity squared, is equal to 2 times the acceleration times the distance. There we go. Yeah. So he says, we are all getting 9s, Jeffrey. Yes, you are. I reckon if you're here now, you're in a good chance to get one of kind of the top grades. Okay, that's basically all we need to know about that. Oh yeah, one more graph. This one here is one that you have to know about. This is a velocity time graph that looks a bit like this. And this is, I think, the hardest graph in GCSE physics. I said the video title a bit clickbaity, so these are the hardest topics. This one here maybe shows an object that is accelerating until it gets to its terminal velocity. Now, let's look at this part of the graph, this part, and this part. Now, let's imagine the kind of standard physics example. Let's imagine a paratrooper, maybe somebody in one of the elite British Army units. Maybe when they first jump out of an aeroplane, they might start accelerating towards the ground, but they've got a certain value of weight, okay? And their weight does not change during that jump. So the whole time, their weight is going to be the same. Now, as they leave the aircraft, they're not moving very quickly, and that means there's going to be no drag force. So this is what happens at stage 1. They've just got their weight acting down. At stage number 2, you can see that their velocity has increased, and as their velocity increases, so does the drag force. So maybe the drag force has increased compared to how it was before. And so this is what happens at stage 2. And then they get quicker and quicker and quicker. And as they speed up, the drag force increases even more until the drag force is equal in size to their weight. So this point over here is 0.3 on the graph. Now I'm going to go to a different colour to show the size of that resultant force. So here, well, let's put some numbers in. Let's imagine they've got a weight of 1,000 newtons. So let's imagine they've got 1,000 newtons downwards as the downwards force. Initially, because there's no upwards force, that means the resultant force is going to be equal to 1,000 newtons. Okay, and of course that force will act on their mass, causing an acceleration. Then of course this one here, let's imagine we've got a 500 Newton drag force. Now their resultant force is going to be equal to 1,000, take away 500, which is 500 Newtons. So as they've got quicker, the resultant force acting on them has got smaller. And at this point here, where their drag force might be equal in size to their weight, the resultant force is going to be equal to 0 newtons. Okay, and now coming up, we start to look at Newton's laws, and we can write Newton's second law as F is equal to ma. Now, they're going to have the same mass the whole time, maybe 100 kilograms, but basically they've got a big force here, so there's a big initial acceleration, And as they get quicker, the acceleration gets smaller as the resultant force gets smaller, until at position number 3, there's going to be no resultant force. Now they're still moving, but there's going to be no more acceleration. And at point 3 is where they're undergoing terminal velocity. So they're falling at the same rate and they're not getting any quicker. This could be the parachute regiment, or it could be 7 Power RHA, Royal Horse Artillery. So yeah, does that help? Right, okay, don't worry about a bit of D-Day stuff. It's always good to have some kind of airborne warriors kind of talked about. And that's what I did before I was a physics teacher. So yeah, doing like night jumps and jumping at like 600 feet and stuff. So all good, exciting stuff. That's what you can do with like a STEM degree. You can go to university. To be fair, you can do that without having any qualifications at all, to be honest. But yeah, you can do exciting things after you've done your GCSE physics in the future. Okay, the next thing then we're going to talk about is nicely going on to Newton's laws. Basically, there are 3 laws. Okay, the first one is what we've kind of basically talked about there with this example over here. Here we have no resultant force on an object, and so if the resultant force, which I'm going to just do in green, is equal to 0, then basically there's going to be no acceleration, and that means an object will either stay at rest or continue moving at the same velocity. So this is an example of Newton's first law. Newton's second law is kind of an example of what we had over here, where if there is a resultant force on something, then it will accelerate. And so basically, again, this is where you've got maybe one object, there's a resultant force acting on it, and that causes the mass to accelerate. Okay, so this is where you might have a resultant force acting on something, and then the object accelerates. And basically what we can say is the acceleration is proportional to the force and inversely proportional to the mass. So you increase the force on something, it accelerates more. You increase the mass of something, it accelerates less. Okay. For some reason it says that. Oh yeah, sorry. I think it just said the chat was disconnected for a sec. Then is everybody okay? We're all good. Okay. The last one is Newton's third law, and this one is one which is maybe understood a bit less. And this is about the force between 2 objects. And basically, whenever 2 objects interact, this is what AQA say, whenever 2 objects interact, the forces they exert on each other are equal and opposite. So Newton's third law is about 2 things. So the red object will exert a force on the blue object, and the blue object will exert a force on the red object. And so this is about the interaction between 2 different things. Okay, then we've got a bit about stopping distance. Stopping distance is going to be, and this can be to do with a car, it could be to do with a bicycle. So basically there will be a certain stopping distance that an object takes to come to a complete halt. So this is going to be the stopping distance, and it's made up of 2 things. First of all is we have the thinking distance, and that's a distance that maybe a vehicle travels between you seeing an obstruction in the road or some kind of danger. That's how far you travel before you put your foot on the brake. And then we've also got over here the braking distance. And the braking distance is affected by things like the condition of the tyres, the condition of the brakes, the road surface, and of course both of these are going to be affected by how quickly you're travelling. Thinking distance is going to be affected by alcohol, drugs, so that could be illegal drugs or even legal drugs that people have been prescribed as medication. It could be due to tiredness, distractions, all sorts of bits and pieces. There we go. Somebody said, yeah, so are we all good? Somebody says slow mode was turned on. Yeah. The mass of a car is a factor as well. Yeah, so for example, if you've got something which is more massive, it will have a greater braking distance because it will have a greater kinetic energy that has to be transferred into the thermal store as you put your foot on the brake. There you go, a bit about stopping distance. And then there's the next thing we need to look at is momentum. Yeah, so the next bit is very much more of a higher, if you're doing a higher tier part of the exam. So you do need to know about momentum. Now, confusingly, we do use the letter P for momentum, and P is equal to M multiplied by V. So think of momentum as the quantity of motion, and it's a little p for momentum. We also use little p for pressure, so physics can get a bit confusing. It comes from, I think, impetus, or like impulse. So think about, that's what I think that's the Greek, but basically that's the quantity of motion. And because we measure mass in kilograms, and of course we measure the velocity in meters per second, the units for momentum are kilogram meters per second. And because momentum is a vector quantity, so it's got a direction, like left or right or up or down or plus or minus, that also means that momentum is a vector quantity. So it not only has a magnitude, but it also has a direction in which it's acting. And then we've got define the conservation of momentum. Basically what this means is that the momentum before a collision or an explosion is equal to the momentum afterwards. Okay, so that would mean if you had maybe two objects that collided, if you knew each of their individual momentums, you could add them together to work out the total initial momentum, and that would be equal to the total final momentum of those two objects. Is it Peter? Peter, meaning to seek or to go towards. I thought it was Greek. Yeah, I reckon. I think I need to just check this up. Tell you what, I will check. I'll check in a minute. I'll check at the end, but it's either Greek or it's Latin. It's definitely one of these. Okay. Somebody AI said that real quick. Yeah. Do you know what? Somebody could have a good check. Where do we get the letter P for momentum from? Yeah. Let's find it. Okay. Right. The next thing is kind of based on this. We do know, and I'm just going to go through this kind of thing, which is useful if you're doing triple physics. We know that force is equal to mass times acceleration, but we know that acceleration is equal to the final minus the initial velocity divided by time. And if we put this A into that equation, we can say that the force is equal to the mass times V minus U over T. And so that would mean if we kind of multiply this out, that force is equal to mv minus mu over t. And mv is going to be our final momentum, mu is going to be our initial momentum, and therefore we can say that the force is going to be equal to our change in momentum, so delta just means change in momentum, over the change in time. And this is a much better way of expressing Newton's second law. We can basically say that for Newton's second law, the resultant or net force is proportional to the rate of change of momentum. Okay, this equation here is not on the data sheet. Basically on the data sheet, they say it's equal to delta V over T. So that's just the size of the change of velocity. But of course, we know from the equation it says V squared minus U squared equals 2AS, that V is your final velocity and U is your initial velocity. So that's where that equation comes from. And basically I just put it in there to kind of sort of show how to get to this. And of course what this means is that if you have something where you increase the collision time, so imagine we've got the same value for the change in momentum, but you do it over a much larger time, we're going to get a much smaller force being applied to something. So that's why you have crumple zones, that's why you have airbags, because all of these things, they increase the collision time for the same change in momentum, and that means they decrease the size of the force that an occupant or somebody feels. Okay, somebody says, we can't hear. You can hear, Jeffrey, Cheesy Beans. Yeah, hopefully this is all working. How long is the live stream? The live stream is going to be longer than I thought it might be, because we've basically only done so far the stuff on forces. So I reckon we should be done by 7 o'clock tonight. So it's like 5:45 at the moment. I reckon we'll be done by 7. I don't want to do it any longer than that, because I think 2 hours is long enough just to kind of sort of revise most of these bits and pieces. Yeah, right. Is this for AQA combined? Yeah, there's basically parts of this are for AQA, parts of it, well, all of it's for AQA. Everything I cover will be useful for combined, and then I've got the extra bits that you need to know about if you're doing triple. But hopefully by this point, you understand what's double and what's triple, or what you need to know for your exams. Okay, somebody was asking, I apologise, I didn't answer everything, was about the parallelogram rule. So imagine you've got two forces which aren't at 90 degrees. Imagine we had two forces like this. What's the resultant of those two forces? Well, basically, we can take this, because it's a vector, and add it end to end to the other vector. So that's one of them, and then the other one looks like that. Okay, so we basically kind of added these end to end. And then what we can think about is a parallelogram. So let's think about a side kind of related to that, and a side like this. This is a parallelogram, and the resultant of these two things is equal to the longest part from the start to the end of that. And I think this is what we often look at. Sorry, that wasn't drawn very well, was it? Basically, this red thing here might be our resultant force of these two other forces over here. And so we're really sort of using like a parallelogram to kind of add one to the other. So another way this might be represented, maybe we've got these forces acting in these directions. If we kind of basically draw in a kind of parallelogram, so we draw in a side parallel to this, which is kind of up here, we draw another side parallel to that over there, then the resultant of these two things is going to be equal to this diagonal of the parallelogram. Okay, because what we're doing is effectively taking this arrow, we're drawing it up here to get that side, and that's what we kind of call a parallelogram of forces. Okay, is everyone all good? People are saying they can hear. This is good. Okay, right, let's keep the chat nice. Okay, let me have a quick sip of tea. I'm just going to go and open the window, and then what we're going to do next is we're going to be looking at waves. Lovely topic, looking at, well, I'm quite happy with those. I've got some transverse and longitudinal waves. So we're going to cover this for the next part, and then we're going to do the electromagnetism, and finally end with a little bit of space. Okay, right, so let's have a look at waves, which, by the way, is going to be relevant for everybody if you're doing OCR, EdXL, you're doing IGCSE. And I reckon my plan is we'll finish by 7 o'clock, which then gives you plenty of time to kind of have a good night's sleep, do any final revision, ready for your exam tomorrow. So we've got longitudinal transverse waves. So basically what waves do is they transfer energy. And so maybe we've got a wave that's transferring energy in this direction. So this is a direction of energy transfer. Now, some waves have got particles that might oscillate backwards and forwards about a fixed position. And if they're oscillating backwards and forwards, it's not that the particles go anywhere, but they just pass this energy transfer on. And so here, if you've got particles which are oscillating backwards and forwards, parallel or in the same direction as energy transfer, this is what we call a longitudinal wave. And if you've got particles that are oscillating at 90 degrees to the direction of energy transfer, then we have a transverse wave. And you need to know about the difference between them. Longitudinal has got many examples, including sound and also ultrasound. Whereas transverse waves include the whole of the electromagnetic spectrum. So that's like radio all the way through to gamma. Okay, so you need to know about examples of both. Oscillate just means to vibrate around a fixed position. So oscillate just means the particle is going to be going backwards and forwards or side to side around a fixed position. Okay. I think that vibrations are different to oscillations because something could be vibrating in all different directions. It could be moving as it's vibrating, whereas oscillating is just going backwards and forwards about the same position. So I think the word oscillate is a better thing when it talks about waves. Yeah. Okay. You also need to know about things like amplitude, wavelength, and frequency. There are two graphs that we can use for this. So if I just draw the kind of normal standard graph, the distance from its equilibrium position is going to be its amplitude, and the distance between one peak and the next subsequent peak, or trough to trough, or wherever it might be, this distance here from one wave to the next successive wave is equal to the wavelength. Okay, and that's provided we're looking at a graph where we've got maybe the distance up the side and the distance along the bottom. Okay, so that there is equal to the wavelength. There's another graph which is similar, but this is what you might see on an oscilloscope. On an oscilloscope, you might have a graph that shows a wave, but it's got the time along the bottom. And if it's got the time along the bottom, the distance here, maybe from a peak to a peak, trough to a trough, or the midpoint to the midpoint, this distance here is equal to the time period. So capital T is the time period. We can still have the displacement here, but this is now about the oscillation of a single particle. So this is a thing that you might see on an oscilloscope. And if you know the time period of the wave, we can say that the frequency is equal to 1 over the time period. Now the time is measured in seconds, and we could give this the unit of seconds to the -1, but the common unit that we give this is the hertz. That's going to be the number of cycles per second. Like, subscribe and ring that bell. Thank you very much. Yeah, definitely. By the way, if you are doing A-level physics next year, definitely subscribe, because I've got so many videos where I could basically teach you the whole A-level physics course without any other teachers. I reckon I could almost do that. I know that lots of people have used that. A lot of people have used my other videos to kind of sort of self-teach over the last few years. Yeah, and hopefully I'm saving your grades, or I'm basically increasing the grade boundaries. We'll see how it goes. Okay, that's all good. And I suppose the other thing you need to know, the things that link the wavelength and the frequency and the speed of the wave together, is the equation that says the wave speed is equal to the frequency multiplied by the wavelength. And we use lambda, which is a Greek letter, lambda, to represent the length of that wave. Okay, right. How do you define a rarefaction and compression? Okay, so from these graphs here, both of these graphs could be either a transverse or a longitudinal wave. You can't tell, because basically this graph here just shows, you know, the oscillation of one particular thing. Often what you might see is with sound waves, you might see a diagram that shows the particles, and maybe they're spread out, and then they're kind of, the particles are more compressed together. And this is very difficult because it's trying to show like a moving object. So the oscillations are just going to be side to side, but the energy transfer is maybe in one direction. And here you've got a compression where you've got the particles closer together. Here you've got a rarefaction where the particles are further apart. It's probably easier to see if you've got like a slinky, and then you see like the coils get closer, or the turns on the coil get closer together at the compressions, and they're further apart at the rarefactions. Okay, let's keep going. So all that stuff is pretty straightforward, but then a lot of the wave topic is to do with basically a lot of the wave topic here is for people who are doing triple science. So if you are doing combined, ignore anything here that's got a blue bit to the side. But a lot of this stuff here about waves being about reflection or refraction, a lot of that can be ignored by lots of people. Okay, so first of all, waves can be reflected, absorbed, or transmitted. Construct ray diagrams to illustrate the reflection of a wave at a surface. So this is a nice simple diagram. If you have a surface, I'm going to do one side with this hatched line to show that's like the non-reflective side. This is the way that we standardly represent a mirror in physics. if you've got a ray of light coming into the surface, the point where it meets is where we can draw in a normal line, and the normal is at 90 degrees to the surface, just like earlier when we talked about forces, the normal contact force is at 90 degrees to that surface. So if you had a ray of light that came in, always draw your rays with a ruler and label the direction that that's going. This angle here is the angle of incidence, and for something which is reflecting off a mirror, the angle of reflection here, R, is going to be the same as the angle of incidence. So if that came in at 45 degrees to the normal, this would come out at 45 degrees to the normal. So this is what we have with reflection at a mirror. Yeah, cool. Okay, right. How do you know what the normal is? Basically, the normal is just going to be 90 degrees to the surface. Okay, so for example, if you had a curved mirror, let's imagine we had a curved mirror like this, and we had a ray of light that hit the mirror. Which way would it reflect off it? Well, the first thing we're going to look at is at this point here, we're going to look at which direction that surface is. So basically, this is the direction of the surface. It's basically like a tangent to that curve. And then my normal line would be 90 degrees to that surface at that point. And so here, this is going to be my angle of incidence. And so my angle of reflection would be the same. So my angle of reflection, R, would be the same as the angle of incidence. And that's the way it would actually bounce off. So you can use the same information that we have up here if light were to hit a curved surface, because it doesn't matter about the rest of it. All we're thinking about is where the light hits the surface, the normal line is at 90 degrees to that. Okay, okay, cool. The next thing then is sound waves. You need to know a bit about sound, you need to know about ultrasound, and you need to know, I guess, a little bit about things which are partially reflected. So sound and ultrasound are both longitudinal waves. Low sounds are about 20 hertz, and the upper threshold is about 20,000 hertz, or that's 20 kilohertz. Okay, so basically that's audible sound, and that's what we call a sound wave, and that's like the audible range of humans. Anything beyond that, so basically 20,001 hertz plus, is what we call ultrasound. Okay, so these are waves which are still mechanical waves, as in there's particles actually oscillating backwards and forwards. They're still mechanical waves, they're just at very, very high frequencies. And we can use both sound waves and ultrasound to look inside things. So if you use a sound wave, we might have a sonar system, which is used to send a sound wave underwater, and then we detect when it echoes back and it bounces back. Or we can use ultrasound to look inside the body or inside other objects. And what these have is basically, imagine we've got something where there's like a crack inside this. At the top, we have something called a transducer, and this is the thing that can basically make an ultrasonic wave, and it can detect the ultrasonic wave. So it's going to send out a wave into the material, and when the wave gets to a crack or a change in medium, then what happens is some of the wave bounces back and some of the wave moves through, and it's going to bounce off the other surface. Now, what we see on a graph is maybe when the transducer first gives out a wave, we get a big signal like this, and then as time goes on, the wave is moving and it moves down to the boundary, and then it bounces back, and then it moves up to this point here where it's detected again. So what we have is maybe the signal sent out and then the signal received. Now the other part of the signal, it kind of comes out from here, it moves past the boundary, it keeps going, it bounces off the end, and then it comes back, and then we detect it another short time later. Okay, so maybe this is what we might see. Now I'm going to call this T1. That's the time that it takes for the signal to go from here down to here and back up again. And T2 might be the time it takes for the signal to come from here all the way down and back up again, and that's going to be T2. Now, of course, if we think about the distance, this is the thing that there's so many times students get it wrong. T1 is the time for it to go from here to here and back to here. And really that means the time to go from here to here is going to be equal to half of T1. Does that make sense? So basically you can either half the time on this graph here, or you can make sure that you account for the distance down and the distance back. And if you know how quickly something travels, we know that the displacement is equal to the speed times time. That means if you know how quickly the wave is travelling in that material and the time it takes to either go back down and come back up again, or just to travel half that distance, you can work out the distance to a crack. Okay, somebody said here, top tip, bring a phone into the exam, you can watch back the stream. Yeah, okay. Right. Is there a rule against bringing the equipment for practicals into the exam? I don't think there is. I think though, if you came into the exam with like a semicircular glass block, I don't think there's a rule against it, but I think, although to be fair, a semicircular glass block is basically a protractor, isn't it? Basically, you know what you need. I don't think there's any rules that means you can't have scientific equipment as long as you can't record anything on it. Yeah, good question. Right, the other thing that you need to know about is seismic waves. So here we have the Earth. Here we've got the molten centre, and let's imagine there's an earthquake here. What happens is that waves come out, and some of the waves can basically travel through the centre of the world to the other side. Some of them can't, but what these do is these basically spread out. And what we have are different sorts of waves that can travel through the Earth. And by looking and detecting these waves, there's like this kind of shadow zone where we only get waves which are transverse. No, we only have, in this region here, this is called like the shadow zone. And in the shadow zone, you only get waves that can actually travel through the liquid core. So basically, these are the longitudinal waves, because it's only the waves that travel backwards and forwards that can pass through a liquid. Around here, we only get the waves, or we can only detect some of the transverse waves. And basically, these ones here, the longitudinal waves are the P waves, and the transverse waves are what we call the S waves. Okay, so S waves, the secondary waves can only travel through solids. The primary waves, which you often detect first, can travel through solids and liquids. And that's because we've got basically this molten liquid core in the centre of the Earth that we can't see directly. It's too far to drill down to. So the reason we know it's there is by looking and analysing these waves. Okay, yeah, cool. Right, let's keep going then. Yeah, electromagnetic waves. So you might have heard the song. I hope you've heard the song. There's a whole spectrum of waves that have some similar properties and some different properties. You've got long wavelength, then you've got the wavelength gets shorter and shorter. You do need to know the order of these. Okay, so basically over here, everybody has heard the song, good. So you've got radio waves, then you've got micro, then you've got infrared, visible, ultraviolet, we've got X-ray, and then you've got gamma. Okay, and basically I've drawn this separate bits because it's not like one long wave, it's like different parts of a whole spectrum of waves. We've got a long wavelength over here, down to a short wavelength over here, and then we've got a low frequency all the way up to a high frequency over here. These ones here are more dangerous because these ones are all ionizing, and you need to know about the dangers of ultraviolet, for example, causing damage to skin or potentially causing skin cancer. X-rays are much more ionizing. Of course, gamma, you did alpha, beta, gamma when you looked at radiation for paper 1, so that's all good. So you need to know about some of their uses. The thing they all have in common is they all travel at the same speed in a vacuum, which is 300,000 meters per second. Sing the song. Okay, I think Debbie's already got it there in capitals. Gamma rays. I can't sing it. I need to. What I really need to do, right, and this is something I never got around to when I was working as a teacher, was wouldn't it be amazing if you had the whole school to sing the song like an end of year assembly? Because often there might be hymns being sung at Christmas time or Christmas carols. Imagine if you had the whole school singing the EM Spectrum song in a massive assembly. Teachers out there, if you're a teacher, please make this happen. I'd love to see that a whole school of 1,000 people singing the electromagnetic radiation song. What is the song? It's the electromagnetic spectrum song. It's like, Google it. Well, after this, go and Google the EM Spectrum song. Yeah, right. The next thing is you need to know about refraction, often demonstrated with like a semi-circular block, and then you have a ray of light. It's a bit hard to do this in the dark. Let me just turn off the studio lights. So, I've got a torch that okay, imagine there is light coming out the end of this torch. For some reason, oh, there we go. You can maybe just about see that. If you have a ray of light that hits the block, it basically goes straight through and out the other side. This is because the angle of incidence is 0. As you start to move it through different angles, can you just about see that? Basically, the angle of incidence here is different to the angle of refraction, and that's when the ray of light actually starts to bend more. Okay, so what we have then is refraction is when a ray of a wave basically changes direction because it changes its speed. So here we might have a rectangular block of glass or perspex or plastic. You send a ray of light into this, and of course we always have the angle of incidence between the incoming ray and the normal, and the normal is at 90 degrees to that, and then I've got the normal continuing down here. If the ray of light, for example, were to slow down, it would bend like this, and so the angle of refraction is smaller than the angle of incidence. And then as it went from this point here out into the air again, we'd have another normal line. Now this is the angle of incidence, and the angle of refraction is going to be larger. So here, the angle of refraction is bigger than the angle of incidence because it's speeding up. So it's going quick, slows down, and then it speeds up again. And a way to think about that is to think about what we call the wave fronts. So the wave fronts are basically like a top-down view of the wave. And what happens is that one side of the wave hits this medium before the other, and that basically drags it down. And that means the wavelength decreases as it's going through here. It's going to have the same frequency, but we've reduced the wavelength. Then this side here is going to hit that first, then it all speeds up, and then we have an increased wavelength and an increased velocity. Now the frequency stays the same, so the frequency is what determines the colour. So for example, this green light that I've got over here, the fact it's green when it turns on is because, there you go, it's got some green light here. The fact that this is green light is because of the frequency, and we know that the wave speed is equal to f lambda. And so if you've got something where the velocity is smaller, but you've got the same size frequency, we must have a correspondingly smaller wavelength of that light. And so as the wavelength shortens, that's when it kind of basically brings the light towards the normal, and that's where we get that. Okay, is that all good? Okay. Right, okay, let's keep going. So that one there, a couple of diagrams here showing refraction. Then, of course, you need to know a bit about changes in atoms and their nuclei when that results in EM waves being generated or absorbed. Okay, so you can have an atom, so you've got like your protons and neutrons in the middle, and then around the outside of this we have electrons in different shells. You know that, you've done it for chemistry, but if you had an electron down here maybe, and one down here, what we could do is we could actually get this electron to move to a different energy level. And what you can do is if you maybe irradiate it with some light. So we're going to shine green light onto the atom, and the electron could move to an outer energy level where it has more energy. But it doesn't stay there for long. As the electron drops back down to the lower energy level, it gives out some light. And for example, that's why when you did your flame test in chemistry, different types of elements gave out different colours of light. So it might be red, it might be a purple or a lilac colour, it might be like an orangey colour. And so what you can do is you can take the electrons, you can expose the atom to electromagnetic radiation. That makes the electrons move to a higher energy level, and as they drop back down to a lower energy level, they give out more light or other types of electromagnetic radiation. So if it gains energy, it goes to a higher level, a higher outer shell of the atom. As it drops back down to a lower energy level or a lower shell in the atom, that's when it then gives out some energy. Okay. Right. Somebody says, can I do microphones and loudspeakers? You can't find a single video explaining it well, says Alex. Alex, have you looked at GCSE Physics Online? I'm sure I've got a video there. Okay, I'll come on to that. But I'm going to do a bit about lenses first of all. Okay, right. Lenses basically use refraction to bend light. There are three things that you have to know about. So the first one is where you've got a type of lens that is called a converging lens, and that means all the light that passes through it, if it's got parallel rays of light coming towards it, it basically bends that light towards the focal point. So this point here, F, is the focal point, and it's at a focal length from the lens. Okay, now first of all we're going to imagine we've got an object over here, so I'm going to call that O. And if we think about what happens to rays of light which are maybe coming off from the top of this object, the first ray of light, let's just imagine this one here is coming in parallel to this principal axis down the middle. Now this ray of light, because it's moving parallel to this, it's going to be refracted, bent, and then it moves through the focal point, and then it keeps going in a straight line. So I've got the first ray of light that I've drawn in red. Okay. The next ray of light is going to come from the top of the object, and it's going to go through the centre of the lens. Now earlier I showed you this picture of refraction, and what we can see is that the ray of light coming in is parallel to the ray of light coming out. Now that just means that we can basically approximate this as a line that goes straight through these parallel sides, and that's why if we think about a ray of light hitting the centre of the lens, where you've got parallel sides to that lens, it basically goes through and it keeps going in the same direction. So that's the second ray of light that I've drawn. Now what we then get is an image that appears to be where these rays of light cross over, and so this thing here is my image. I've got the object, which is upright. I've got an image, which is upside down. The other thing about it is that we can look at the size, and maybe the image is smaller than the object. And also, we've got real rays of light that cross over. So what we have here is a real image, because it's where actual rays of light cross over. So, somebody says, the frequency of bad physics jokes hurts. Yeah, I know. Thank you. Second time. It is worth it though. Second one though, is this bit here, the stuff about lenses is only for those of you doing higher tier, doing triple physics. Now that's the first one that you need to know. The second is basically the same kind of lens. So we've got a converging lens, there's going to be a focal point over here, but now I'm going to draw my object over here. Now we do exactly the same as we did up here. The first ray of light, we're going to draw parallel to this kind of central line on the diagram. So it's going to go through the lens, and of course then it's going to go through the focal point, and it's going to keep going. So that's the first ray of light that I've drawn, in this case in red, just to kind of make the two different lines very clear. Again, if we think about a ray of light coming from the top of the object through the centre of the lens, it's just going to keep going like this, which is what we had before for the other green thing, ray of light there. But now you can see these two rays of light appear to be moving apart and they're diverging. So we sort of follow them back to where they appear to come from. So I'm going to do that with a couple of dotted lines. And where the two lines cross over is where we see the image, which is this point over here. Now we can now see that we've got an image that is bigger than the object. So this is what we have with a magnifying glass. And we don't have actual rays of light crossing over. We've got what we call virtual rays. And so this is what we call a virtual image, which we couldn't project onto a screen. We could only look at if we're maybe looking through the lens in this direction. And effectively that's what you do with a magnifying glass. You find the image is on the same side as the object. Okay. Okay. So I've just seen a new physics joke. Why did the pirate go to Proxima Centauri? He wanted to spend 4 years at sea. Oh, do you know what? I'm going to have to take a picture of that so I remember that. I'll put it in. Is it a bit sad? But we do have like a big physics teachers kind of WhatsApp group with Eyes at Physics that people have been putting jokes in recently. I'll put that in there. God, is that what my life has come to? Anyway, you need to know about these things. We have a converging lens. When the object is far away, we get a small real image. When the object is close, we get a virtual magnified image. Yeah, okay. The next one is you need to know... Oh, no, sorry. The next one is you have a... again, the same kind of central line. But here, I'm going to put a diverging lens. And I might have a focal point here and here. Now with the diverging lens, if you've got parallel rays of light, they don't come together, but they split apart and travel further away. So they don't come together, they diverge away. Now let's imagine we've got our object over here. Again, the same pattern as before. We're going to do a ray of light that is parallel to this axis. But now it's not going to go through the focal point, but it's going to move away. And we've got another focal point on this side. And effectively, if we draw a line from here to here, that's the direction that that ray of light moves off at. The other ray of light is going to go from the top of the object through the centre of the lens, and it's going to keep going in what is supposed to be a straight line. Apologies about my poor drawing there. And where the two rays of light cross over is where we have the image. So here we've got the image, here we've got the object, and you can see it's a virtual image because we've got a virtual ray of light crossing a real ray. So this is a virtual image that is smaller, but it is upright. And what's the point in that, I hear you say? Well, basically, that's the kind of lens that you get with lots of glasses. So these, because I'm short-sighted, if you look at what you can see through my glasses here, you can basically, this thing here is my object and the image is what I see through my glasses. So what I see through my glasses, or what you can see through this glasses lens, is smaller than the real thing, and it's virtual because it's not really there. You can't pick it up, you can't project onto a screen, but it's on the same size of the lens as the object. So this one here, short-sighted glasses have diverging lenses in them. Okay, what's a nuclear physicist's favourite meal? Fish and chips. Very good. Thank you everybody for repeatedly posting that. Yeah. Thank you. Right. And that's basically... Oh, here we go. We've got a bit more here. A lot of this stuff here is kind of quite text heavy. I'm sure you've got like learning checklists. You can find this over at GCSE Physics Online. A bit about black bodies and stuff like that, and how basically a black body is an object that basically absorbs 100% of the radiation that is incident upon it. So any radiation coming in, it absorbs it all. And then it's a perfect emitter, and it emits 100% of that radiation as well. And it's called a black body, and we can often approximate stars and things to this. Now, if something is at the same temperature, it's going to be absorbing and emitting the same amount of radiation. So imagine you've got something which is quite hot, and it absorbs 100 joules of energy, it's going to emit 100 joules of energy. Now that can then obviously tie in to the work on global warming, where if you've got the Earth, which is maybe absorbing more energy than it's emitting because of the increase in, and obviously you did this for chemistry paper too, when you looked at the kind of greenhouse gases, things like methane, as well as carbon dioxide and water vapour. Basically, a lot of the radiation that comes in is absorbed by the Earth's surface during the day. It's re-emitted at night, but it isn't all escaping, and that's why it's now getting hotter on average than in previous years. Okay, right. That is the end of the waves bit of the course. And now, very shortly, we're going to go on to looking at magnetism and electromagnetism, which I think is probably one of the harder parts of the course. But it's not impossible. Okay, so we're going to look at permanent induced magnetic fields, and also we're going to look at transformers, generators, dynamos, alternators, motors, all of that good stuff. Okay, right, excuse me. Okay, I've got myself more paper. Somebody said this topic, race to 27, this topic is my downfall. Don't worry, you'll be absolutely fine. So, magnetism and electromagnetism. It starts out easily with basically permanent magnets. You've done these before, and in its kind of simplest format, if you just have like a permanent bar magnet, which has maybe got a north and a south end, the magnetic field lines go from north to south. I'm going to sketch these in. Of course, if you were doing it, you would be doing this in pencil. And they're going to go from the north end around to the south end. So I'm going to put some arrows to show that direction. So this is maybe our permanent magnet, which is a magnetically hard material because it stays magnetized. You also need to make sure you're using the correct hand, because we can also have magnetic fields that we can turn on and off. And magnetic fields are produced by moving electrically charged particles. So if you've got electrons moving in a wire, we've got this conventional current I, and surrounding that wire we have a magnetic field. So this is like a 3D image, and if I draw some of the field lines, they're concentric circles centered on the wire, and the circles get further apart like this. And to work out the direction, we're going to use our right hand and we're going to use the grasping rule. Okay, so this in this case is basically going to have field lines which are going anti-clockwise if you were to look down it. So that is a current in a wire producing a magnetic field. Now what we can do is we can take this wire and we can wrap it into a coil. Now this coil, there's basically one coil of wire, and if you've got a coil of wire that can carry a current, that we call this a solenoid. So a solenoid is a coil of wire that carries a current, and what you'll notice here is that we have a number of turns. So I guess we've got 1, 2, 3, 4, I guess it's like 4.5, but let's say we've got a number of turns of wire. Now, if you have a current going up through this and then down out this way, we can then draw the effect of the basically lots of these kind of concentric circles all on this bit here. And what we'd see is we'd see field lines where they are uniform in the middle, and then they kind of come out at the ends like this. And so you basically have the same shape as the magnetic field around a bar magnet, and we can use our right hand grasping rule again if the current's going this way through that, that basically this might act like the north end of a magnet, that acts like the south end, and so the field lines are going from north to south, and then they're going from south, then they're sort of going this way around that thing. So basically this is a magnetic field that we can turn on and turn off. So this is very simply an electromagnet. When you've got electricity, we have a magnetic field. And we could put a solid, soft iron core in there. That would then, basically make this stronger. So that's basically what we mean by an electromagnet. Okay, Captain Physics versus Physics Online. Who would win in a fight? I don't know. I don't know. Okay, good question. I guess I'm formally Captain Matheson, I suppose, for a bit. So I guess the original Captain Physics, who knows? Okay, right. But yeah, Captain Physics, if you're watching, say hello. We get to do some collaborations together if you're watching this. Right, so basically, permanent magnet, then we've got induced magnets over here. Now that's basically all you need to know about it, because if you know about this, then this kind of sort of leads on to everything else in this topic. So let's see what we need to remember. We've got, yeah, here we go, the magnetic field lines around different bits and pieces. Okay, the next thing is about the motor effect. Okay, now the motor effect is basically you put electricity in, you get motion out of it. Okay, so basically you put electricity in and then you get motion out. Okay, so the motor effect, often seen with maybe a kicking wire, and there's lots of examples where if you had maybe the north pole of a magnet over here, and then this bit here was the south pole of a magnet. This is basically like between the north and the south pole of things here. We would have magnetic field lines going from one to the other. And if we had a wire that was placed in between the two things, and we put some electricity into it, so let's think about conventional current, this is where we're going to use your left hand to predict the direction of the force on that wire. So the first finger is your magnetic field going from north to south. The second finger is going to be the direction of the current, conventional current, moving in that wire. So we've got first finger field, second finger is conventional current, and my thumb is pointing down. And in this case, there would be a force acting down on that wire. So this is, you put electricity into that wire, and then the wire would move down in that magnetic field, so we get motion out, which is why it's called the motor effect. And that's what Fleming's left-hand rule can allow you to predict. Okay, so okay, let's see what people are saying. People are, is this, oh, here we go. We've got the Physics Online fan club. You should get t-shirts, yeah, absolutely. Yeah, right. Okay, so maybe I need to do some more. Okay, there we go. Mr. Salas, I met him for coffee the other year, actually. There's lots of people I need to meet, actually. I think basically what we need is a massive YouTube teacher collaboration with like every physics, biologist, chemist, maths, English teacher. You know, we'll get Kettle Maths on, we'll get Mr. Salas English, we'll have everybody basically. We just need to do some like massive collaboration. Maybe I need to try and get that sorted for next year. Exam QA, yeah, I saw his live thing the other day. Yeah, right, so basically this is the motor effect when you've got current in a conductor, or when you've got conventional current in a conductor, there's going to be a force acting on it. Now we take this idea and we basically can build it more into something which is useful, which would be an electric motor. Now this is going to be a very simple electric motor. We've got the north and the south poles of a magnet. So of course there's going to be a magnetic field between the two. What we then have is either we have a coil of wire like this. Okay, and there might be a number of turns of wire on it. But of course, if we've got the current going in this way, it's going to go up that side, come to the end, and then come back the other way. So thinking about what's going on, we're going to have the same direction of magnetic field, but we've got the current either going this way or that way. And that means on this thing here, one side might experience a force down, and the other side might experience a force upwards. And what that means is this thing here, what we call an armature, starts to rotate. And so you might have this on an axis that can rotate. And what we then need is something at the end to break the circuit and then reconnect it every half a turn. And what you have is if you've got a DC circuit and you've got a motor, what we use is a split ring. Okay, so the split ring is basically a ring of copper, and it's got a split in the middle, and so it's basically like two C sections or C-shaped bits of metal. And of course, this thing here is going to be rotating. Now there's also going to be sometimes called a brush on each side, and this just means that we can have something that stays in contact with the metal. And then this thing here is basically connected into your circuit. So you might have your power supply up here. And of course, if this is a small kind of standard cell, then that's going to be positive and that's negative. So we're going to have the current going in. So this is the direction of current coming into this side, and then current comes out that side. Now, this bit here is what's connected to each side of the wire in this coil over here. And it means that after it rotates through 90 degrees, it breaks the circuit and then it reconnects it. So this circuit here, effectively this side is always going to be positive and this side is always going to be negative. And that means you've always got the current going up this way and then back down that way. So you've always got a force here going down and the force on that side is always up, and that's why the motor actually spins. Okay, so this thing here, you've just, even if you don't fully understand it, remember this for the next 24 hours. Basically, DC circuits, where you've got a motor, use a split ring. And the whole point in the split ring is that it basically breaks the circuit and reconnects it as this thing is spinning. So you always have the current going the same direction in that magnetic field, and that allows the motor to keep rotating. Okay, now that's normally, I would say at GCSE, 99.999% of the time, if you've got a motor, it's going to be a DC motor. Okay, now the other thing you can do is you can take this setup and you can replicate it. I'll do this one bigger so it's a bigger diagram, so hopefully it's clearer to see. So we've got a permanent magnetic field. So here again I've got like the north and the south end of a couple of magnets. Okay, so we've got the field lines like this. And then what we can do is we can have a piece of wire that goes into it. So there might be a number of turns on it. And what we might do now is, rather than putting electricity in to get motion out, what we're going to do for this one is we're going to put motion in and we're going to get electricity out. So we're basically, rather than transferring maybe some energy transferred electrically into kinetic energy output, we're going to put kinetic energy in, and we're going to get some electricity out. So this is where we actually have to turn this. So we're going to apply a force to this, and we're going to move a conductor in a magnetic field. Now when we do that, what we do is we induce, you have to use the word induce, we're going to induce a potential difference. And of course, if you've got a complete circuit, that then means that this will then induce a current. Now, this is called the generator effect, and this device here is now a generator, because what we're doing is we're generating an output. And often what you have with one of these is one side of this is connected to one ring, and the other side, let me just see if I can draw this. Oh, this is going to go badly. And the other side is connected to a ring. Oh, that's it. So basically, oh, that's an awful diagram. Basically, this side here is connected to that bit of a ring. So that's going to be on that side. And the other side, I'm going to draw in like a blue colour, is connected to this bit here, which I'm going to draw in blue. I need to make a proper Lego model really to kind of show this. Now, one of them is going to go sort of this way in the circuit, the other one's going to go that way, and this then kind of basically comes into our electrical circuit. Now, when you've got a slip ring, this is basically like two completely circular rings side by side, and this gives us an AC output. And you remember from the work we did on electricity that AC is an alternating current. So basically, a slip ring gives an AC output when you've got a generator, but we tend to use a DC split ring when you've got a motor. Okay, yeah, drawing a motor for the millionth time. Why are slip rings in alternating current? Basically, this means that this side here is going to be moving. If we were to maybe rotate this say this way round, when this bit of wire goes down, it's going to cause this to have maybe a negative value of current going this way. And then when the other side goes through it, it's now going to cause the current to move in the opposite direction in the wire. So what's going to happen is the electrons are basically going to be alternating side to side in the wire, as either this side or that side is positive or negative, depending which is going through that field. And so basically what we do is we get an output, either for current or potential difference, that looks like this over time. Okay, so sometimes it's positive, sometimes it's negative. And if you were to spin this thing quicker, we would be cutting more field lines per second. So the output would go up, but the frequency would go down. So imagine we spun it quicker, we get a much larger output voltage, and there'd be a higher frequency of output as well. Okay, can a generator induce DC current? Yes, it can. So this is basically a generator. There are two types of generator. Now at GCSE they just tend to call it a generator. In reality, you could have something called a dynamo, and that gives, like the magician, a dynamo gives a DC output, because that would use a split ring. Or you have an alternator, which is often what you have in a car to charge up the car battery in like a conventional combustion engine car. This gives an AC output, and that uses a slip ring. Okay, so basically there's just two different types of generator. Dynamo gives a DC output using a split ring, and alternator gives an AC output using a slip ring. Okay, right. How do you get it spinning it? Yeah, so basically, how do you get this thing spinning? Well, basically the best way to do it is on the end of this, you attach like a massive kind of turbine blade. And this turbine is the thing that you get spinning, and the spinning turbine causes the generator to move round. Now you could get the turbine blown by the wind, so that's why we've got like these big wind turbines. You could have steam going through it, and the steam pushes the blades round, and you heat up water to make steam by burning coal, oil and gas. You might use nuclear fission to heat up water to make steam to turn the turbine. You could have waves that are crashing past it. You could have water going down the hill. You could pump water underground to geothermal. All of these things that you've learnt about for paper 1 are ways to get the turbine moving. The turbine's connected to a generator, and that's what generates our electricity. Okay, right, let's move on from that. I want to do one last bit that combines all of this, basically. So this thing here, if I draw it like this, you'll know exactly what we're talking about. Okay. Okay, that's going to be the primary side, and over here, I don't know how many times I've drawn this diagram now this year. Here we go. This is going to be the secondary side. So this is a transformer. We've got the core, which is made out of magnetically soft iron, so it can become magnetized and demagnetized really quickly. Over here we've got the primary coil. There's one coil with a number of turns. We've got the secondary coil, which is one coil of wire with a number of turns. Now in this case we've got a step-up transformer, because you go from a low to a high number of turns. If it was the other way round, and that was the primary coil and that was the secondary, we'd have a step-down transformer, because we step down the number of turns. Now the number of turns, or the ratio of the number of turns, is going to be the same as the ratio of the potential differences. So for example, let's say that had 3 turns and that had 5. We've got a ratio of 3 turns to 5 turns. Now imagine we had an input potential difference of 30 volts. This would then mean that the output voltage or potential difference would go up to 50 volts. So the number of turns is proportional to the potential differences. But of course, we don't get anything for nothing. The power in is going to be the same as the power out. And we know that the power, electrical power, is equal to VI. So what this means is if we think about over here, the power in, let's say that's equal to V times I. That's going to be the same as the power out, which equals V times I. But if we increase the potential difference, we must decrease the current. So imagine we had 20 volts times 2 amps in. We then have 50 volts times 1.2 amps on the output. So although you might step up the potential difference, we step down the current going from in a step-up transformer. Okay, so basically this is the whole point, is that we use transformers in the national grid because you want to step up the potential difference and decrease the current to transmit it through the cables at a low value of current to reduce any heating losses. And at the other end, you have a step-down transformer where we step down the potential difference, we increase the current to a usable format for use in homes and offices. There we go. That's basically what you need to know about transformers. And of course, what we have is you need to have an alternating current here, because an alternating current means we have a changing magnetic field. That changing magnetic field is transmitted through the iron core, through the centre of this, and then you've got a changing magnetic field next to a conductor, and that then causes there to be a potential difference induced in the secondary coil, which will then cause an alternating current in that secondary circuit. There we go, that is transformers. Okay, right, then we've done the generator effect, that's all good stuff, we've done that good stuff. Right, I think we're now on to the last little bit of space, which is an absolutely lovely topic. Sorry I can't answer everybody's questions, but I reckon we can get through this in about 18 minutes. Yeah, right, space. You need to know about, to be honest, not much about the Milky Way galaxy where we are. You don't even need to know the order of the planets. I'm sure you do. But the main thing is we're looking at stars. And there's the formation of stars, which is basically just this collection of dust and gas. And everything's attracted to everything else in space due to the force of gravity. And over a long time, things which have mass attract other things that have mass. And this is happening in a star-forming region called a nebula. So let me just zoom in on that. Now, depending on the size of the nebula, this determines the life cycle of that star. So first of all, small stars, like our sun, do this. They form a protostar, which is basically the collapse of this dust and sort of gas and stuff. And it all basically gets hotter and hotter as its gravitational potential energy is transferred to the kinetic energy. And of course, temperature is related to kinetic energy. And it forms a protostar. And then it spends most of its life in what we call a main sequence phase. And this is where we've got the force of gravity pulling everything in. And there's a radiation pressure due to the nuclear fusion that's happening inside the very centre of that star. And the two forces are balanced, and it stays stable like our sun. At the end of its life, when it starts to run out of fuel that it can use to fusion together, the star basically swells up, the outer surface cools down to this reddy colour, but the whole star is much, much bigger at the surface, and this is called a red giant. And then eventually, when the fusion stops, what's left behind is a very hot, dense core. And so it's a white dwarf because it's very hot, but it's a lot smaller. And then eventually, that just cools down to become a black dwarf. So that's basically the life cycle of a low-mass star like our sun. Now, bigger stars, which have a lot more fuel, they basically have a bigger force of gravity pulling everything in. So we have a greater rate of nuclear fusion, which means the stars burn hotter and they have a shorter lifetime. So heavy stars, they burn through their fuel quick because there's a bigger force pulling everything in. And at the end of their life, they become a red supergiant once they start to run out of fuel. And this then can collapse where the outer layers basically bounce off the kind of the dense central core that's left behind. And there's this massive explosion called a supernova. And then what's left behind, there's going to be very, very dense, and there's no nuclear fusion going on, and this forms a neutron star, which is basically the same density as a nuclear nucleus. And if it's really massive, it can actually form a black hole where basically everything collapses in on itself, and then our normal physics rules don't apply anymore. Okay, so so basically you need to understand, and this is a good 6-marker to practice, what's the life cycle of a star like our sun? What's the life cycle of a star much larger than our sun? Okay, loudspeakers and microphones, I'll come back to that in a second. I'll come back to it at the very end, okay? Right, so where does a resistor live? In his own ohm? Very good, thank you. So if I see a joke, I will try and say it if it's one I've not seen before. Okay, so basically, if you've got a star, there's going to be a large force of, basically, the gravitational force of attraction is pulling everything in. Okay, so there's got to be this inwards force. Now, for the star to be stable, it's what we say is an equilibrium, so the forces are balanced. So there's going to be an outwards force as well. And this outwards force is what we call radiation pressure. And it's basically because we've got lots and lots of nuclear fusion going on. So the fusion, as again you learnt about in paper 1, this is joining together of light nuclei. And effectively this is, we join hydrogen, which are the simplest things. And basically there's so much energy here that all the electrons are kind of stripped off the atoms to make this kind of ionized gas, a plasma, which is mainly hydrogen, which is just basically protons. And if you collide enough protons together through a whole series of reactions, eventually we can turn them into helium. And it's this process of nuclear fusion that releases energy, E equals mc squared. So hydrogen is joining with other hydrogen and other hydrogen and other hydrogen to make helium. And that's basically the fuel that's kind of providing the energy source for these things. Now, when it's in this stable phase, the radiation pressure out is equal to the gravitational collapsing force in, and the whole thing is going to be stable. Yeah. Then, of course, you need to know a bit about how the force of gravity can lead to changing velocity but an unchanged speed. Okay, so this is the reason why the Earth doesn't fall into the sun. Here's the sun, and here's the Earth, and the Earth and the sun are attracting each other. That's an example of Newton's third law. So the force of the sun on the Earth is the same as the force of the Earth on the sun. But the key thing is that at any point, the Earth is moving at a velocity that's at 90 degrees to the direction of the force. And that means it ends up going in what's supposed to be a circular path. And so the velocity of this object is at 90 degrees. So this is the direction of its velocity. That's the direction of the force. And this resultant force does cause the Earth to accelerate, but it doesn't make it faster or slower. Instead, because it's accelerating it by changing its velocity, it's changing its direction. So we've got the force of gravity causes the Earth to move in a circular orbit, just like around the Earth we've got the moon, and the moon is going to be going in this kind of circular path around the Earth, and of course the sun is going to be going in a circular path around the supermassive black hole at the centre of the Milky Way. Okay, so we've got lots of things moving in circular paths where we've got the force at 90 degrees to the velocity of that object. Okay, yeah, it's the perpendicular to the force. So you can say that the velocity is perpendicular to the force in which it exerts on the sun. Yeah, okay, circular-ish path. Right, the final bit is you need to know about the Big Bang. And there are 2 bits of evidence for this. One of them is redshift, and the other one is CMBR. Okay, now I did this earlier when I was helping somebody with their revision. Imagine you've got a wave, and I'm going to draw a wave with my hand like this. And this is the wave that we see. Okay, now I'm going to draw the same wave again, but I'm going to move the paper. So if I draw the same wave, but now I move the paper, we can see that the wavelength increases. And this is what happens with light from distant objects. The light is stretched because the object is moving relative to us. And we call this redshift. Of course, you know from the EM spectrum that when you've got visible light, we've got different wavelengths of visible light. And you've got things which have a short wavelength, like violet, and then you've got things which have a longer wavelength like red light. And so if the light from a star or a galaxy has been stretched, it's basically stretched out the wavelength into the red part of the spectrum. And so what you get is redshift when light is stretched. Equally, if I had, again, I'm going to draw my wave here. If I had that wave and I was actually moving the paper towards the pen, or moving it towards the pen, we actually see that the wavelength is compressed. So this is basically blue shift. And I don't know why it's not called violet shifted. We say that the light is blue shifted if something is moving towards us. So for example, parts of Andromeda, the waves, maybe some stars or parts of the galaxy are moving towards us, and that light is blue shifted. So redshift is evidence that things are in the universe are moving away from us. And what we find is that as we look at stars which are further away, the amount of redshift also increases. And the redshift is related to the recessional velocity, how quickly those things are moving relative to the Earth. And that's of course related to the distance that things are away. And we see this relationship here. The further away something is, the greater the redshift and the greater that object is moving away from us. And that's because if we were to look at all the objects, if this is the Earth, things which are close by have a recessional velocity a bit like this. Things which are further away have a bigger speed of recession, there's more redshift, and things which are even further away are moving away from us even more. And basically, no matter where you start, what we find is that everything in the universe is moving away from everything else. And this then gives us evidence for the expansion of the universe. The other thing that we have is cosmic microwave background radiation. Now, in the very early universe, the radiation that we had was basically lots of high energy gamma rays, and they had a very short wavelength. But as space has got bigger and everything's expanded, their wavelength has stretched out, and it's gone from sort of the gamma part of the spectrum into the microwave region of the electromagnetic spectrum. And so we have microwave radiation in every single direction that we look in the universe. And that's because in the early part of the universe, when it was really hot and dense and energetic, there was gamma rays everywhere. Okay, so CMBR is cosmic because it's kind of coming from space. It's microwave because that's the part of the EM spectrum it's in. And then it's background because everywhere we look, we can see it. So if you look up into the night sky, in the summer, in the winter, whatever time of day, every direction we look, it's in the background to everything else. And it's radiation because I guess it's microwave radiation. So that's cosmic microwave background radiation. And this is basically the energy from the time of the Big Bang that's just been stretched out as the universe has expanded. Okay, how much paper does he have? Do you know what? I've gone through, I've been doing masterclass. I've done huge amounts. By the way, when you're doing A-level physics, I'll help you with masterclasses and live streams and things as well. But basically, there's, I think I've got through about 8 reams of A3 paper and probably about 12 reams of A4 paper this year. So it's shocking how much I spent on paper and how much I've kind of got rid of. But it will all be recycled. So, fingers crossed something useful happens to it. Okay, and basically, what else do we need to know? So the Big Bang assumes that everything is like, basically the universe is expanding. But the more recent information we have is that the rate of expansion is increasing, and this is probably due to things like dark energy that are basically making the rate of expansion of the universe increase. Do we know why that is? No, we don't. We're still looking into it. And that was GCSE Physics Paper 2 in about 2 hours. The one thing I haven't done, as people have asked me to do, is a bit about the difference between a loudspeaker and a microphone. So I'll do that and then we're done. So we're almost done. Right, so a loudspeaker What a loudspeaker does is it basically takes some electricity that comes into it and it basically makes motion. Okay, now that's different to a microphone that basically has motion coming into it and then electricity comes out. It's really a bit like, the way I see it, is a loudspeaker is a bit like a motor, and a microphone is using like the generator effect. So it's like the difference between a motor and a generator is the same as a loudspeaker to a microphone. So a loudspeaker, basically what we have is a coil of wire. You know, I'm going to do a permanent, we've got a coil of wire like this, and what we can do is we can have a signal that comes into this coil of wire. Now, of course, when you've got a current flowing into this, we then just have an electromagnet, don't we? So we can use our right-hand grasping rule, and basically if you've got a current going in, we're going to have like the north and the south end of this electromagnet. Now, if you put a permanent magnet near to this, or indeed what you'd have is a coil of wire wrapped around this actual permanent magnet, if there's like the north end at the top and the south end at the bottom, if the current is going in one direction and we've got the sort of the magnetic field around this, it's either going to attract the magnet or repel it. Now, if we had an alternating current inside this coil of wire, that means the current is going to be changing direction, and that means this thing here is going to be either attracted or repelled from this coil. And what we can then do is basically put on a large kind of cardboard kind of cone shape above it, and as we have an alternating current, that's going to be changing the direction of the magnetic field, and that's going to cause the motor to oscillate up and down, and that means the cone here is going to oscillate up and down. And what that then does, I haven't drawn this very well, but that then produces a sound wave that comes out from that cone, because all a sound wave is a mechanical wave of particles oscillating backwards and forwards. So there we go. This thing here is a loudspeaker. A coil of wire next to a permanent magnet either repels or attracts the permanent magnet with the same frequency as the alternating current, and that's going to make the cone go back and forwards. So for example, if you connected this up to a 50 Hertz AC signal, we'd have a 50 Hertz oscillation of the magnet, we'd have a 50 Hertz oscillation of that cone, and then we get a 50 Hertz sound wave. Now, with a microphone, we do the opposite. We get sometimes like a diaphragm or a small cone, like this. We attach this to a permanent magnet, so you've got like the north and the south end, and we put this near to a coil of wire. Now what we're doing now is we have a sound wave that's going to come through the air, and it's going to cause the cone to oscillate up and down. So now the cone starts oscillating up and down. That's going to make the magnet oscillate up and down. And now we have a magnet moving inside a coil of wire, and due to the generator effect, this means that we either have a current induced this way or a current induced that way. So this now makes an alternating current that's going back and forwards in that wire. And of course this just comes into an electrical circuit where we can detect the electrical input, and then we can like amplify it and then use it maybe in a phone, maybe in like a microphone for a camera, for example. And basically we put motion in, we get electricity out. So a microphone is like an anti-loudspeaker and vice versa. There we go. I think that's it. That is GCSE Physics Paper 2 sorted. If you are doing A-level physics, I'll see you next year. Actually, I'll see you in a few weeks' time. If you are doing A-level, I have these books for you to work through over the summer. It is the best transition work you can do from GCSE to A-level, and I guarantee if you do this book, you will find A-level physics really straightforward. I've got links to the book and other resources I have beneath this live stream. The other thing is, yeah, good luck tomorrow. If you're not doing A-level physics, fair enough, but you only need to remember the stuff I've talked about for the short term. So basically in 20 hours time, you don't need to remember it again. So work hard for your last exam, check over your notes, have a look at some easy questions just to give yourself the confidence. You can rewatch the live stream if you want. I do have plenty of other videos on YouTube, like all of AQA in I think 2 hours, whatever it is. So yeah, am I going to get a break now? Extra galactic. Do you know what I did? I had probably the hardest week last week, where I worked 12-hour days every day, and I've been in my office. I came in about 7:30 this morning to edit videos because I did a load of filming for the Ogden Trust to make some videos for their teachers. So we made 36 videos last week, which I now need to edit. So and then I'm going to, what am I doing this week? Going to London on Wednesday to an AQA conference where they're going to talk about exams. We're going to meet all the people from AQA, and then do some other physics things. Yeah, it's just like different work, but like maybe less live streams. But yeah, I've worked hard. I'm sure you've been working super hard. You've been doing like a month of exams now, over a month, and it's probably a well-deserved rest that all of you have once your exams finish. So yeah, thank you everybody. I'll leave it there basically. Somebody says, thank you so much for your resources. I've been so helpful. Sad this is the last live. Soraya, yes, I've seen your name come up so many times in my live stream. So yeah, I hope it all goes really well. Yeah, thank you everybody. It's been great having you here. If you haven't already done so, do like and subscribe, all that good stuff. And if you are doing A-level physics, or if you know people who are, do point them towards my resources where I can hopefully help you for the next couple of years. Right,